In this video, we're going to take a look at where some of our kinematic equations come from based on some values that we have in our motion table. So if you're unfamiliar with the motion table and how this was filled out, please take a look at the other motion table video in which we go through and fill out all of these values. So if you recall, the first thing that we filled out in our table was our final velocity at each time interval. So 3 seconds referred to 3 seconds having elapsed since I started my stopwatch, and in this condition, when I started the stopwatch, my object was moving at 100 meters per second with an acceleration of negative 20 meters per second, so that every second that elapsed, it lost a velocity of 20 meters per second. So when we got our final velocity, not only did we have to take into account our acceleration, but we had to take into account our initial velocity. So I think it's pretty clear from looking at this table that all we did is we took our initial velocity, which even if we look at a time interval of 3 seconds, because we're considering our initial velocity to be at the instant we started the stopwatch, our initial velocity was 100 meters per second, and there was a change of 60 meters per second, which I think is pretty clear. We can get 60 meters per second if we multiply this 20 by this 3. In this case, because our initial velocity is a positive value, and our acceleration is negative, meaning the opposite direction, when we added them, we ended up with a smaller number, right? So what we said is our final velocity was our change in velocity. Our acceleration times some time is going to be a change in velocity plus our initial velocity. Pretty straightforward, I think, how we got our final velocity for each time interval. The next thing that I think becomes pretty clear is how we got our average velocity. Our average velocity describes the average from the start of our stopwatch, so from the instant 0. So that after 1 second has elapsed, our average velocity was 90 meters per second. After 2 seconds, it was 80 meters per second, right? Because we're slowing down. Notice the average velocity is smaller than our initial velocity in this case, and it's larger than our final velocity, in fact, somewhere in between. It turns out that when you're dealing with a constant acceleration, the average velocity will be halfway in between both values. So we can find it very easily by adding our two velocities, our initial and our final, together and dividing by 2. That's going to be our average velocity. Now the next question is, how did we find our final displacement? Well, let's begin with an equation we're already familiar with, which tells us our change in displacement is equal to our average velocity times time. So if we were to look at, for instance, this 3-second mark, our change in displacement would be our average velocity, which was 70 meters per second, times the amount of time that was our average velocity, which was 3 seconds, which would be 210 meters. However, you can see we're actually at 260 meters. Well, why is that? It's because we did not measure from the initial position of our object. We measured from some other point. So we started with an initial displacement of 50 meters. And actually, I just realized that this table is filled out wrong. It should say 50 all the way down. Okay? So what we did is we added this 50 meters to our change in displacement. So 50 meters plus 210 got us that 260. So now, if we take a look at the actual equation, what it's going to say is that our final displacement is equal to our change in displacement plus our initial displacement. So if I rearrange this equation, it says delta D is equal to our average velocity times time. This is the equation that you are used to seeing, and it is in fact the same. On your reference table, when you see this D and this T, they are talking about changes in displacement and changes in time. So they're actually accounting for both an initial and a final displacement. Even though it doesn't look that way, they are. Okay, so let's go back to this equation that we found on the other slide. And now I'd like us to recognize that an acceleration times a time is a change in velocity. Okay, then we've got our average velocity equation, which we added them both together and divided by 2. And now what I'm going to do is I'm going to take this whole expression and plug it in for our final velocity. So recognize this initial velocity plus our change in velocity is the same thing as our final velocity. Okay, so I rearrange this. Our VI's add together. The whole thing is over 2. And now what I can say is that my average velocity is equal to my initial velocity, because the 2's cancel, plus 1/2 AT. This average velocity equation is now the same as this one right here. Okay, except for now, instead of needing a final velocity, we could calculate an average velocity given an initial velocity, an acceleration, and a time. The next equation we're going to look at is the one that relates our final displacement to our average velocity, time, and initial displacement. Recognize, a velocity times a time is a change in displacement. So really it says final displacement is equal to change in displacement plus initial displacement. Now the first thing I'm going to do is I'm going to combine these, and I'm going to write them just as D, because this is how your reference table shows. It does not show a final and an initial, it shows just one D talking about a change. It means a change in displacement. The next thing that I'm going to do is I'm going to plug in this right up here for our average velocity. Okay, I'm going to pause this for a second. So what I did is I took this average velocity and I plugged in this formula we found before. So this whole expression just reads average velocity. So our change in displacement is going to be our average velocity times our time. The last thing I'm going to do is I'm just going to distribute the time. So now we've got our initial velocity times time plus 1/2 AT squared. And this is an equation that you are going to find right on your reference table. Okay? And all it's saying is that when you have an initial velocity, you are going to have some displacement over time. But that displacement is going to be affected if there is an acceleration. And that 1/2 AT is just your average change. That 1/2 just means an average. That's why it's there. Because from before, when we took an average, we needed to divide by 2. And then we multiply by time again, because really this is some velocity. So when we multiply by time again, we end up with some displacement.